Well, good afternoon, everyone, and thank you for joining us today for our Black History Month event featuring Dr. Christine Darden. I am Tanya Ennis, the director of the Bowes Center in the College of Engineering and Applied Science, and my co-host is Dr. Brian Argro, the chair of the Ann and H.J. Smead Aerospace Engineering Sciences Department in the College of Engineering and Applied Science. The Bowes Center and the Smead Aerospace Engineering Science Department are co-sponsoring today's Black History Month event. Thank you for being here. So today we will have a presentation by Dr. Darden, and Dr. Argro will facilitate the Q&A sessions throughout the time that Dr. Darden will speak. And so feel free to add your questions in the Q&A down at the bottom of your screen, and we will do the best that we can to pose questions to Dr. Darden, who will then respond to the questions. So it is my distinct pleasure to introduce the legendary Dr. Christine Darden, a pioneer, a trailblazer, a hidden figure, an intellectual role model, a brave genius, a distinguished woman. Dr. Darden is from Monroe, North Carolina, and began her career at NASA as a human computer at Langley Research Center, where she developed complex programs and performed complex mathematical analysis. Dr. Darden served as the Deputy Program Manager of the TU-144 Experiments Program and was appointed as the Director in Program Management Office of the Aerospace Performing Center, and managing air traffic and other aeronautics programs. Dr. Darden is the author of more than 50 publications in the field of high lift wing design and supersonic flow, flap design, sonic boom prediction, and sonic boom minimization. In 2019, she was awarded the Congressional Medal of Honor. Additionally, Dr. Darden is featured in the book Hidden Figures: The American Dream and the Untold Story of the Black Women Mathematicians Who Helped Win the Space Race. I could spend the entire time talking about Dr. Darden's life, accomplishments, and awards. However, I know that you would much rather hear it from her. Dr. Darden inspires me to be the best that I can be, and I really appreciate her being with us today. Before we welcome our honored guest today, I would like to hand it over to Dr. Brian Argro to share a little bit about our time together. So Dr. Argro.
Thank you, Tanya, and again, welcome to Dr. Darden. What we propose to do is have Dr. Darden give her talk, and then we will have a Q&A session where I will look at the questions that are in the Q&A that you all will put on onto the Zoom. That's at the bottom of your should be at the bottom of your what you're looking at, and then after that, depending on how much time we have left, we want to end at about 90 minutes, and officially, and then maybe have a few more minutes afterwards if there's still interest for people to talk to Dr. Darden. And depending on how much time we have after the Q&A, I might take the honor of doing a bit of an interview with Dr. Darden. So with that, I turn it back over to you, Tanya.
Thank you. And so with that, let us welcome our honored guest, Dr. Christine Darden. I am going to share my screen to show your presentation for your talk.
Okay. Thank you. Thank you. It's great to be here with you all this afternoon, and I really appreciate the invitation to speak at Colorado University. I guess some people have wondered about the title of this presentation, 4P Journey to NASA. I chose that title because of it is actually the 4 Ps that I think helped get me to NASA. It is a formula that I used to help me make up for some weaknesses that I had in high school. I went to a fairly small high school, segregated high schools, all at home, and only took algebra in my class there in my hometown. And when I was in the 11th grade, my parents sent me to a boarding school in Asheville, North Carolina, in the mountains of North Carolina. And the only class in mathematics that I could take there was plane geometry. That was the only other class that they had. And I took the plane geometry in the 11th grade, and I absolutely fell in love with it. I really enjoyed the class, and I realized that I didn't have a lot of mathematics in my background. The last year I was in the boarding school, and there was a slide here on that. The last year I was on the at the boarding school, my job was, we had duty works there, and my job was to collect a morning newspaper and to take it to the library so that everybody could have access to the newspaper in the library. And when I picked up the paper that morning, October the 5th, 1957, it had the Soviets have launched a spacecraft into space. It is flying at 18,000 miles per hour over our heads. It has crossed over us 4 times in the last 24 hours. And so this was, of course, was Sputnik, when Sputnik was launched, and I was a senior in high school. And I remember the tremors that went through the school systems. I remember the tremors that went through the people at NASA and everywhere else who said, how in the world did the Russians beat us, or the Soviets beat us into space? It was quite a shock to the people at NASA. And of course, that's when we started, I guess, trying to encourage our students to take STEM classes, to take the mathematics, to take the physics and things like that. And so that was my introduction into space. And it was quite a great introduction, and I really appreciated it. So anyway, I graduated from high school with that background, leaving a yearbook that had a space theme, since that's what we chose. And I came to Virginia to Hampton Institute. And I'm thinking I'm going to major in mathematics, since I fell in love with mathematics and plane geometry. But then as students were coming in from Washington, DC and New York and Richmond, Virginia and Virginia Beach, Virginia and everything, these kids all had calculus and analytical geometry and trigonometry and all of those classes. And here I am with algebra and plane geometry. And so I'm thinking, gosh, I guess I'll have to start at the bottom and just kind of work my way up. But then my father called me and he says, Christine, I think you should get your degree in teacher education and major in your mathematics and your physics as the areas that you would teach and everything. And so I said, Dad, I'll think about that, because I had, as I fell in love with mathematics in high school, I had started thinking about what my passion was. And I decided, I think math is my passion. And the one thing I did also like in high school was physical science. And so it might have been the combination of the math and the physical science that was more my passion. And so the P's that I had, first of all, you wanted to find your passion, determine what your passion is, because I think when you're working for your passion or something that you really love, you actually would work a lot harder than you might if it's not something that you don't particularly care for that much. So my P1 was perceive of yourself in that career, perceive of yourself as a mathematician. I did. And I actually taught the plane geometry class when we did a day when we exchanged with the teacher, and I taught the class. Then the second P is plan what you need to get there. Well, to be a mathematician, I needed to take a lot of mathematics. That was a pretty easy question. I needed a lot of mathematics since I didn't have much in my background. And then P3 says, okay, you've got a plan now. You've got to get all this mathematics. You start preparing, work your plan. How do you get that mathematics? And P4 says persist, keep going, don't stop. And I will add this now. I actually talked about this with some Girl Scouts in California 2 or 3 years ago. And in the process of working with them, I learned what their charter was. They considered, they says, we want our Girl Scouts to have these characteristics when they graduate from Girl Scouts. We want them to be a go-getter. Go after what you want. Don't wait for others to initiate everything. Make sure you can initiate some things that you want to see initiated. That's for the G in girl. The second one was be an innovator. If you run into a detour, solve your problems, find the way around the detour, and keep going. So it's GI as go-getter and innovator. And then the third thing is be a risk taker. That means get out of your comfort zone sometimes. And that means you need to kind of suffer a little bit when you take this risk, and you might not be sure of what the outcome would be. And then the fourth one, the L, says be a leader, be able to influence and lead others. And this kind of completed the 4P dream. And I wanted to talk to you about this now, because actually thinking through what I really liked and how I was going to get there and all of that, I believe that it actually helped me get through a lot of those steps. And so now I am at Hampton. My father has called me, and I decided, my dad wanted me to be able to get a job when I graduated with my BS. And so I decided I was going to do what my dad said, because I knew some students didn't always get jobs when they finished college. You would hear parents talking about that. So I said, okay, Dad, I'm going to do what you say. I'm going to major in teacher education. But another thing that I am going to do is, during the 4 years that I will be earning my teacher education certificate, I am going to be earning electives in my classes. I've got 4 years, and I will actually earn so many classes that I can take for free without having to pay extra funds for them, because they will be my electives. And what I'm going to do is, my last year, when I have all these electives, I am going to use all of those electives to take high-level math classes that I don't have to graduate. And that is what I did. One of the things that I did, okay, as soon as I was starting out, I was going to have to take analytical geometry, and analytical geometry was taught at the same time as modern algebra, which I had to have for the education degree. And the students came to me, a number of students came. There were two classes of analytical geometry. One had a really good teacher, and they all gave him praises and everything. The other class had a teacher that didn't teach too well. And that was the class that I would have to take if I took modern geometry. And so I decided I wanted the good teacher in analytical geometry, which meant that I couldn't take modern geometry. So I took the analytical geometry, everything went well, and I went through the rest of my years in undergraduate school. And when I got to my senior year, it suddenly dawned on me that I hadn't taken modern geometry yet, and I had to have that to graduate. So now what do? It was being taught. I wanted to take an advanced calculus class, and I could not, and it was taught at the same time as the modern geometry class. And so I said, What I'm going to do now is I'm going to the registrar of the school and I'm going to ask if I can take both classes. I did that and I was allowed to do that. So they said, okay, you can attend the advanced calculus class and you can only go to the modern geometry class when they are having a test. And so that is what I did for that. But for the rest of my senior year, I did my student teaching in math the first semester. And I took the 4 math classes the first semester. And guess if that was the first semester, one of those classes was the geometry algebra combination. And then second semester, I did my student teaching in physics. And I took 4 more math classes. I graduated with my certificate to teach in Virginia. And I graduated with about 24 hours of mathematics that I did not have to graduate. And went off to the central part of Virginia to start teaching. When I got there, as soon as I got there, a teacher came up to me and said, we are about 60 miles from Virginia State College. And Virginia State teaches people who teach in Virginia, they teach them in-service classes free of charge. And we are going up there Saturday morning to register for a class. We want to know if you want to go. I said, absolutely, I'd love to go with you. So that's what I did. On Saturday morning, I went with the other teachers. We went to Virginia State. I signed up for another high-level math class. And the head of the math department was the teacher of that class. I did that the entire year, my first year teaching, and actually really enjoyed it. It worked out very well and everything. The next couple of years, I actually left that school where I was teaching and moved back to the coast of Virginia and started teaching in another class. And I had gotten married during that time. And at the new school where I was actually the one who went around to the teachers and said, we have a school here that teaches free in-service classes in Virginia. I would like to get some of you all to go with me to Virginia State College to sign up for some classes that you could take, maybe in what you're teaching here in school. I got 1 carload of teachers to go with me. And so we went up and we registered for class at Virginia State College. And we were doing well. Everybody registered for a class. I chose another math class. And we're going through the first semester. Everything went well. The classes this time were on Friday nights instead of Saturdays. And so we would have to work all day on Friday. We would then have to drive 80 miles to Petersburg and then stay in class for about 2 or 3 hours, and then leave at about 10:30 and drive home. So that it was a kind of a hard day, but we got along fine doing that first semester and everything. I thought everything went fine, except at the end of the first semester, every one of those teachers who was with me said, we're not going back to second semester. I said, oh my gosh, oh my gosh. You mean I got to drive by myself at 10:30 at night back home alone on the highway? I don't want to do that. That's not safe or anything. But then as I thought about it, I thought about my 4 Ps. I can't quit. I've got to keep going. And so I decided to do it myself. I would do it all alone and drive up to Petersburg by myself. And so I did that and continued driving alone at 10:30 at night by myself. And when I would tell my students about doing that, I would say, and lots of that time, my head was sort of halfway out the window, so I would not fall asleep. I certainly didn't want anything to happen. And so I finished that year, and I was glad I did, because my husband, who had gone to Virginia State, had gotten a fellowship to get a master's degree in biology. And so then as I was finishing the semester, I said, gosh, it looks like I might actually need to be moving to Petersburg, and we'll need a job here. So the second class or so on Friday night, I went up to my teacher and said, you know, it looks like I might be moving here this summer and next year. And I'm wondering if you know of any jobs around here that I might look into that I might be able to get here in Petersburg. He said, oh, you're looking for a job here? And I said, yes. He said, well, let me take you across the hall to the head of the physics department. He's looking for a research assistant in aerosol physics. So we walked across the hall to meet Dr. Hodkinson. And he told me that he was looking for somebody to do some research, light scattering of non-spherical particles in the atmosphere. And which sounded great to me. And then I found out as I would continue to talk with them that I would be paid enough money, not just to get paid for doing the research, but I would also get paid to earn a master's degree at Virginia State, which I said, oh my gosh, that's great, because I certainly didn't have money to earn a master's degree. But I knew that what I really liked was the mathematics and the physics and the physical science. And so I chose to do my master's degree in applied mathematics. And so I finished my year of teaching and then came and entered Virginia State to work, to do the research and to work on my master's degree in applied mathematics. And I did that for 2 years. And at the end of the period, when I was about to graduate, I went by the placement office at Virginia State and told the young lady I was about to graduate with a degree in applied mathematics. And she looked at me and she said, well, where in the world have you been? I said, what do you mean, where have I been? She said, didn't you know NASA was here yesterday recruiting? I said, no, I didn't know that. She said, well, they were. She says, here, you fill out this application and get it back to me as soon as you can. I'm going to mail it in to NASA. So I took the application she handed me. I filled it out and gave it to her. She mailed it in. 3 weeks later, got an offer from NASA to come to work there on June the 27th. And so that was what I did. I went to NASA. I did not know what job I was getting at NASA, because I don't think I sent any of my transcripts or anything with me. But anyway, I went to NASA and I found out when I got there that I was being assigned to a computer office in the reentry physics branch. The Apollo program had just started. I finished in 67. The Apollo program had started that year. They'd had the accident down in Florida, I guess in December or January, where the first astronauts got killed. And I was sent to the computer office, and it took me a while to find out what the computer office was. But the computer office was when the Wright brothers invented their airplanes. They did not want their airplanes used in war, but during World War I, the Germans, the French, and the English actually worked on their airplanes quite persistently to make them good for war and make them very, very valuable, in fact, for war. And an American citizen went to President Wilson and said, I think you need to find out a way that we can have a coordinated aeronautics program in this country, because now the Europeans and the Russians are actually bettering us in the airplanes and everything. And we need to bring all of our aeronautics community together to do this work. And so President Wilson appointed appointed 14 men to be the National Advisory Committee for Aeronautics. And they were the ones who were going to kind of coordinate this work. They came to Hampton, Virginia, looking for property to build a laboratory. And they built the laboratory, the NACA lab in Hampton, not far from the coast of the Chesapeake Bay. And they started building the laboratory there, and then they started putting wind tunnels in the laboratory. And they hired a lot of male engineers. And so when the wind tunnels started running and they started getting data from all of these wind tunnels, the engineers started complaining, all we've got is a slide rule and a mechanical calculator. You're going to try to make us do all this work from all of this, reduce all this data from this wind tunnels and everything, and come up with reports we can send elsewhere. And the NACA group said, maybe this is a time we can begin to hire women. Maybe we can hire women who have prepared themselves to be mathematics teachers. They could certainly help reduce the data that we're using. And so they did that. They hired their first group of white females in 1935. The other things had happened in 2017. That NACA was formed in 1917. And so anyway, the women came in, and then just before World War II started, A. Philip Randolph, who was a labor worker, a Black labor worker in this country, went to President Roosevelt and said, I think you should actually write an executive order. I think you should take all of the defense companies in this country and say, you cannot have any discrimination in who you hire. And so that opened the door for NACA to start hiring Black females to come into the center and help. And so the first group of Black females were hired in 1943, and Dorothy Bond, who was one of the hidden figures, was in that class. Mary Jackson came in 1951, and Katherine Johnson came in 1953. So the thing that was different then about hiring the black computers was that they apparently some laws in Virginia required that they be kept separate. So the white computers were in one area, and the Black computers were called the West computers, and they were in a different area. And that is how NASA worked for quite a while. So when the Sputnik went up in 1957, that is when the United States started saying, we have got to have a space program in this country. I mean, we need a space program. And then, of course, there were a while of who's going to get this space program. Does the military get the space program, or is it going to go to some university, or just what? Well, they decided that NACA should become the space program. So NACA had a center in Hampton, Virginia. They had a center in Cleveland, Ohio. They had a center in Mountain View, California. And so they took the NASA centers and turned the NACA centers and turned them into NASA centers. And they did away. Now we've got a federal agency, so there was no segregation. So then the computer offices began to integrate with each other. And that is the way the computer office was when I got there. Because when I walked into the computer office in reentry physics, there were white and Black females in that office. The head computer was a white female. And that's the workplace I worked for about 5 years. And I was in that was the hypersonics area, and the engineers in that section, that reentry physics branch, were responsible for giving the conditions of the Apollo capsule coming back into the atmosphere. How fast can that vehicle come into the atmosphere safely? In other words, it cannot get so hot that it would fail, that the vehicle would fail, and it could not come in at an angle such that it would bounce on the atmosphere and go back out into space. And so the wind tunnels around there were actually used to make some of these predictions. And there were some other places that were used to help make some of the predictions also. And I wrote computer programs. Some of the other ladies in the office were just learning to program. I had learned to program in graduate school. And the engineers would bring equations in and say, would you write this program, and would you solve this equation and for these variables? And I would write a computer program and do it. And so I did that for several years for the engineers there. And one day I was talking to one of the other ladies in the class in the office there. And I said, I wonder why all of the women are being put in the computer offices and all of the men are being put in the engineering offices. I guess it's because they have an engineer degree. And he said, no, they don't. The young lady I was talking to said, no, they don't all have engineering degrees. There are several men working in the engineer's office who have mathematics degrees. And I said, oh, is that right? Well, I think that's really where I would really be like to work. And so I asked the immediate supervisor there in the branch about being transferred to engineering. And I was told, no, I don't think that's possible. I don't think you can do that. Wasn't that happy, but I went back to my desk and accepted it and trying to think about what I was going to do. I actually thought about, leaving and going to teach at a university. But then I also thought about maybe going to a higher up supervisor, the head of the hypersonics division. And I said, I think that's what I will do. I think I'll go to see the director of the high-speed aerodynamics division. And so I went to see the director, and I said, I'd like to ask you a couple of questions, if I might. I said, I'd like to know why do a male and a female coming here with pretty much the same background, why are they assigned to such different jobs? The females are put in the computer office where they are supporting the engineers. They're working for the engineers. The engineers tell them what to do. And they don't really do any research or anything. They don't give talks. They don't write papers, and they don't publish papers. If you saw the movie, you saw what a time they were having getting their names just on the outside of as a second or third author of a paper. And because publishing the papers is what led to people getting promoted, they weren't getting promoted either. The men in the engineer's office were given some research to do. They did some research in connection with the reentry problems. They gave talks about what they were doing. They just gave to other people. They wrote papers, and they published papers, and they got promoted. And when I got to that point in my question, the director looked at me and he said, nobody's ever asked me that question before. I said, well, I'm asking you that question now. And after a few more interchanges, I left and went back to my office. And 2 weeks later, I got promoted. I had not been promoted in the 5 years that I had been there. So I was hired as a 9. I got promoted to an 11, and I got transferred to engineering. And that was, so my title went from being a data analyst to being an aerospace engineer. And which changed some of the things I could do. One of the things that changed was I could now take classes. They have a graduate program there that most of the women could not take. Mathematicians could not use this graduate program. But now being titled as an aerospace engineer, I could take classes. I went and registered for the Doctor of Mechanical Engineering with emphasis in fluid mechanics. So I was going to start working on my doctorate because I said, I don't want anybody coming up there and telling me I don't have an engineering degree. I'm going to get one. So I signed up for that class, and I went to my new office right after that. And right before I was transferred to engineering, the SST program, Boeing was supposed to, well, what was happening in this country is, of course, the first supersonic flight was in 1947. And then there were lots of people trying to think about how do we solve this? How do we predict this problem? How does a sonic boom occur? And all of those kinds of things. But during the 60s and moving into the 70s, the English and the French were going to build the Concorde. Boeing was going to build a supersonic transport for the United States, and the Russians were going to build the Tu-144 for the Russians. And so we had these 3 countries all coming up to build a supersonic commercial transport. And commercial means it was going to carry passengers. And so when Boeing was supposed to build the supersonic transport for the United States, they said, well, what we want to do first is we want to fly quite a few supersonic airplanes across Oklahoma City and maybe Chicago also. And we're going to have it such that they would get boomed about 7 or 8 times a day with these military aircraft that have been borrowed, and they're flying over this Oklahoma City. Well, when they started flying, people started calling these phone numbers that they told them that they could call. They called, they would call and say, my sheetrock in my house has cracked. My windows in my house have cracked. My dishes in my house have cracked. You know, you all have got to fix all this in my house. And so the government spent about $1.4 million fixing the people's houses in Oklahoma City because of the flight tests across these huge cities and everything. And it was after that that Boeing decided, we're not building it. We're not building an SST. So that happened. And then immediately after that happened, the FAA, the government in this country passed a law that there could be no commercial supersonic flight across the continental United States. That was in 1971, and that law is still on the books today. And so that's why I heard sonic booms when I was a child, but most of the children now don't hear sonic booms because on the East Coast, most of your airplanes, if they're going supersonic, are out over the water. On the West Coast, they're pretty much over the desert. And a lot of the test places in the country are on the West Coast. And so that is where we were. Well, my first assignment given to me with my new boss was a paper by Dr. Richard Seabass and Dr. Albert George on sonic boom minimization. And what they had done is they had actually collected a lot of the ideas that had come from people like Whittam's F function and things like that. they had brought a lot of these ideas together. I'm going to explain the sonic boom so we could go back to that pressure field. Generally when I'm speaking to students, I'll explain a balloon pop first to them. And I'll say, if we were all in one room and everybody had the same pressure on their ears, which was a kind of a light pressure, but everybody has the same pressure on your ears. If I had a balloon and I blew up the balloon in the same room with you, and I'm putting more molecules in the balloon, the balloon is getting bigger. The pressure in the balloon is getting higher and higher. And so now I take a pin and I pop this balloon. That sets up a motion of the wave going away from this popped balloon in all directions, all over the room. And when that wave hits your ear, the pressure on your ear jumps instantaneously at the same time from what it was originally on your ear to now what it was in the balloon. And you hear a pop because you get this instantaneous pressure change. The sonic boom works pretty much the same way. We've got an airplane going through the atmosphere at about 40,000 feet. And it is going faster than the speed of sound. Now, I don't know the speed of sound everywhere, but here in Hampton, Virginia, at sea level, it's 750 miles an hour. And so we've got shocks coming off of the tail end of that airplane or the engine of that airplane. And they set up their disturbances and they're moving in all directions at the speed of sound. Except now, here is the main shock wave off of this airplane's nose. If you've ridden in a boat and you see the shocks coming on the side of the boat, that's exactly what you're seeing here, except now you see that it's three-dimensional and it is actually a cone on the nose of this airplane. And the shocks that are created within that cone actually are staying within that cone. They're going to the sides and they don't go any further. And so we have just along the edges of this cone, a fairly big jump in pressure, just as you go into that. Now, if you were on the ground in this light green area here in this section, you're in a fairly normal pressure area and you hear nothing. And if this airplane continues to move, when I was a kid, if we heard a sonic boom, we'd go out and we'd look up and we'd see nothing. So that's what would happen if you did that. But as this airplane moves away from here and it pulls the dark green area over you, you hear that sonic boom. That your house hears that sonic boom and rattles and things like that. And so now you get the boom that is heard. It is heard because you've gone from a much lower pressure on your ear outside to, as soon as the edge of this cone passes you and you get into that dark green area on the ground, you hear the sonic boom. And it does have higher pressure and you'll get maybe rattling in your house and everything. And so that's what a sonic boom is. And that's how it's generated from that airplane. And so there were ideas of how do we predict the sonic boom. We can go to the next slide now. So there were thoughts, and I mentioned Whittam's F function and things like that. And so a lot of people had actually come up with some things that would help with this. And so here's an airplane at the top of this prediction chart, which says, okay, a Mach number, when we're talking about how fast airplanes are going, we use the Mach number for the speed of sound. So when I was saying that the Mach number, the speed of sound was 750 miles an hour around here, we would say Mach 1 was 750 miles an hour. Mach 2 would be 1,500 miles an hour, and so forth. And of course, the speed of sound actually changes as the pressure of the pressure in the atmosphere changes, and you get different speeds. So Mach 2 high in the atmosphere would not be the same as Mach 2 almost near the ground. That is because the pressure in the atmosphere is different. Okay, so, but with the Mach number, if this airplane was flying at Mach 2 or 3, then there is an angle between that Mach line, which is the angle that goes back up even with the airplane. That's why the line is diagonal. And so here we step from this front of this airplane to the back of this airplane with these Mach lines, and then let that Mach, the intersection with that airplane, be normal to the airplane. And that's the area that we're going to plot it on the same actual point here. And we do that all the way from the front of the airplane to the back, which is 0 here and 0 there. So the lower curve is the volume, or the volume we get here due to the airplane itself. The other line that we see is generated by the wings of that airplane. The wings of the airplane actually have a curved upper surface of the airplane, curved upper surface. And so as this airplane is flying along very fast, it actually even speeds up. The air speeds up going over the upper surface of the wing. And when the air speeds up, the pressure goes down. So now we've got the pressure on the bottom of the wing where it was with the normal pressure that we started with. But since the pressure has gone down on the upper surface, we've got a lower pressure on the upper surface. Well, if you've got a higher pressure under the wing than you do over the wing, which way is the force on the wing going to be? It's going to be up. So there's an upward push on that wing as you're flying the airplane, and that is generating the lift of the airplane. That's what holds the airplane up. So at the base of this curve here you've got your maximum lift on that airplane. It's an integral all the way up through to that point. So if that airplane weighs 200,000 pounds, then this lift has got to hold up 200,000 pounds. And that's the way it works. Okay, so now that there's an integral equation called an Abel integral equation, which equates the equivalent area of that airplane with this Whittam F function. And so we can now take this area and get the Whittam F function out of it using that equation. And again, as this airplane is now moving, as this F function is moving through the atmosphere, the maximum points of the F function are going to advance, and the lower points on this F function are going to be retarded. And so we get this next curve, which shows you the same curve, but now it's distorted and it's multi-valued. And so you don't want multiple values. And so they actually put a change in pressure there by cutting this F function here in equal, bisecting that F function. You're actually adding the area below here and you are cutting off the area above. And if you notice, what you end up with is this curve here. And you get the pressure going from 0 to that maximum pressure. And you also get a big change in pressure here. And that is what they've always called the N wave, how they measured the sonic boom that was occurring. And that is how they started out trying to predict the value of that N wave. And next slide. So one of the other gentlemen who was thinking about this found out that if you had a large shock, a very strong shock at the beginning of the airplane, you would not get the shocks off of the inner parts of the airplane to coalesce. Now, this sharp-nosed airplane here is like a military airplane. Most of them have a very sharp nose, but look at the shocks coming off of all parts of that airplane, and they are coalescing. And as they coalescing means they are merging with each other. The shocks are getting thicker and thicker. That means they're getting stronger and stronger. So this military airplane gives a very large boom on its N wave here on the line. But then you say, well, gosh, okay, let's look at the blunt-nosed airplane. These shocks are not coalescing with each other. So this very big blunt shock up on the nose of the airplane, it only gets softer and softer and softer as it's coming this 40,000 feet to the ground. And so we get a low sonic boom. But what else do we get on this airplane? We get a lot of drag on that airplane, because if your drag, like if you put your hand out your window of your car and your hand is pushed back. So the drag, it takes more gasoline to fly that airplane into the higher drag when you've got this blunt-nosed airplane. And so this is a paradox that a lot of people thought that, gosh, if it's an efficient airplane, it's going to be low boom. But turns out it's not exactly like that. And that's why it's called the paradox. Next slide. Okay, so what we want to do then now is we want the computer program that I wrote. I took all the equations and I wrote a computer program. First, it was, they were not using the real atmosphere. I added the real atmosphere. And when they first put the volume in that front of that F function, they used a direct delta function. So you had an infinitely thin curve that went up to put all of the volume there. Well, once they decided that, maybe that's not exactly what we want for a low boom airplane, I changed that to triangles, and triangles that could be varied, so that we could actually compare how the boom was changing and how the drag was changing on the airplanes. All right, and then again, we can go from the F function that comes out of the computer program to the equivalent area, just by using the formula, the Abel integral equation that we had before. And with this equivalent area that comes now out of the computer program, what we want to do is design an airplane that matches that equivalent area. So we design the fuselage, we design the wings, and we calculate the lift of that. And what we want to do is for all three of those to add up to the equivalent area that we are trying to match that has come out of the computer program. And next slide. Okay, so now everything's running, and this is a typical equivalent area distribution of a military airplane. This is the area distribution that came out of the code, and we can see some dashed points going almost totally with that area coming out of the computer. And so we've just about got matched that with a design. Next slide. Okay, so here is the design that I made of a Mach 2 airplane. It took a long time to do it. There were lots of iterations on the designing of the airplane. And we had some codes in the branch that actually would calculate the lift of a wing and so forth. So we had help in doing that. This airplane was built out of stainless steel, and it cost about $6,000 or $7,000 because it had to be exact. The thickness on every point of that airplane had to be very exact, and all of the dimensions had to be very exact on that airplane. So next slide. One of my office mates who was working with me on this designed this Mach 2.7 airplane. And you can see that while the wing on my airplane was flat, this wing is cambered and a little bit more difficult to design and to build and everything. And anyway, so we had two airplanes, a Mach 2 and a Mach 2.7. And we decided to build one military airplane to test with these two low boom designs we had. And so next slide. This is our supersonic wind tunnel. It is 4 feet by 4 feet. And in case, if you don't really know what a wind tunnel does, a wind tunnel is in our building, and it's like a box all the way around, big part of the building. And there's a huge compressor at the end of this box that blows the air through this box so that it will go Mach 1, Mach 2, Mach 3, and so forth. Here's the airplane that is mounted in the middle of the tunnel, cross section of the tunnel. We've got it sideways so that the door of the tunnel is actually the ground. And on the ground, we've got pressure probe. So here's a pressure probe here, and there's a pressure probe up in top of this tunnel. And this yellow barrier here actually will move just inside this panel so that this airplane could be moved up forward just a certain bit. Now the air that is being blown through the wind tunnel is meeting the airplane. So now as the air is up to Mach 2, this plane is moved forward. Well, when that plane moves forward, what forms on the nose of that plane? That cone we were talking about, because now the plane is for all practical purposes going faster than just the speed of sound there. And so we get a cone that actually overlaps this pressure probe, and we learn what the pressure inside that cone is. The pressure in the tunnel is measured by the other pressure probe up top, and we can get the difference in the pressure here and the pressure up there by those two measurements. And we would know just how loud that boom would be by the difference in the pressure of those things. Okay, so we actually tested our vehicles. We found out that the data that we were getting out of the wind tunnel, we were getting a much bigger jump in pressure on the military model that we had. And we were getting some differences in these two models that were actually supposed to be low boom models. And we were getting actually a smaller jump in pressure in the two that we had designed. And we said, gosh, this looks like it might actually be good. So next slide. We decided we needed to do a flight test. We said, well, you know, a lot of people don't believe everything. That's just what's in the wind tunnel. And so we actually had considered using a missile to try to do that. That didn't work out. DARPA came in and was started to work with NASA on how that would be handled in this program. And so what we have here is DARPA actually borrowed two F-5 supersonic airplanes from the Air Force. Here is what the F-5 really looks like, and it's not been changed in any way. The second F-5 is in the inset here, in which they have added panels on the outside nose of that F-5 such that the shape of this airplane actually matches that equivalent area distribution. And I will also tell you that when we started all of this about 20 years before, we didn't have the computer capacity and the know-how to write computer programs to calculate all over these, all around that airplane on our computers. But as time passed in this, we started doing more sophisticated programs. We had bigger computers, and our experts in computational fluid dynamics could calculate. And so we actually started, we would design it one way, but we would actually probably change some of the designs based on computational results in this. So we have an F-5 here with no change. This is the boom demonstrator here. This is an F-15, which actually measures some of the signals coming off of this airplane up at the altitude where it is also. And I was on the phone talking to a friend of mine who was in the control room at the NASA center that's in California, near the Mojave Desert. And when the signals came in, we started getting some shouts from the people in the control room. And the shouts were, they got a loud noise from the F-5 that had not been changed. And they got muted the noise from the demonstrator for the boom. And so it was doing the same thing in the atmosphere that it had done in the wind tunnel. And so folks were glad to see the results that they were getting. And that is what we did. And I guess what we went back and reported, that this kind of looks like a porpoise here, and we don't think of a supersonic airplane looking like that. So we kind of reported that maybe we should get some real airplane designers to come up and design something that looks more like a supersonic airplane that goes really fast, and that integrates into that the characteristics of a low boom aircraft also. And some of the companies were asked to do this. You can go on to the next slide. And the only one that did any of the designs was Lockheed Martin, the Lockheed Martin Skunk Works. And this is one of the airplanes that they had designed. And here they don't have just the short front. They've actually given us a very long nose on this airplane. And it uses external vision, because the pilot would not be able to see how to land that airplane without him having access to some other ways to see where he's going and everything. And next slide. So actually NASA decided to issue a contract on whoever had been doing some of these designs to build that supersonic low boom airplane for NASA. Lockheed Martin was the only one that we responded, and they got the contract in 2018, and they are supposed to, they have predicted that they will have it finished in 2021, this year. And once they get it finished, they will actually test the supersonic, or the supersonic characteristics of the airplane, how it is handled in flight and everything, make sure that that's fine. Then they're going to fly over people all over this country and get them to respond to how loud the noise is from this sonic boom. And what we're hearing, I certainly haven't heard it, but we're hearing it's more like a thump, nothing like the rifle crack or the sharp crack of thunder that we are used to hearing with sonic booms. And so they will collect this data. And when they collect the data from all of the places that they have been, NASA intends to take that data to the FAA and ask them to consider a rule change. And if they take the data and the people have responded in such a manner that, yes, we could live with that noise crossing us several times a day and we'd be okay with it, they might change the rules. If they change the rules, then we might have our Boeings or some of the other airplane companies building an airplane like this. And we might have American and Delta and United buying an airplane like this. So you might be able to go to New York and get on a plane and end up in Los Angeles in about 2.5 hours instead of the 4 or so hours. If you were going to try to get from Los Angeles to Australia, instead of it taking 14 hours, it might take 7 hours. Of course, how long it takes depends on how fast the airplane is flying for you to do that. And so this is what I did in my career. And I guess we're ready for questions now. Is that
all right? Thank you. That was a tremendous start to finish, and it's, you know, nothing but congratulations to you for your perseverance, and you know, and we're actually seeing the end result. I mean, it's not like you spent all those years working and then didn't get to see an end result. I mean, you actually are seeing this airplane being built.
Well, you're absolutely right. And I think we mentioned that the other day, that the teacher gets sometimes fairly rapid gratification of her work and trying to teach a child something, because they usually, you know, you see them get, oh, I understand now. That's great. That's great. So it's pretty quick. but to wait 25 or 30 years to get any gratification, it is a long time to wait. But a lot of the things that NASA works on, unfortunately, do take a long time to get it done.
Yeah.
And sometimes the people in NASA don't tell the people in Washington how long it's going to take, because it is going to take a long time. But it was, I enjoyed the career. I enjoyed everything I did. And as I've said, I think I'd said before, I actually got to give papers overseas and attend conferences overseas. And I really enjoyed what I did.
So we have a few questions, and before I get to the questions, I just wanted to tie up the thread. You mentioned Richard Seabass.
Yes.
And
yes.
For those who, or for our students and others here at University of Colorado, may know that Richard Seabass was, my predecessor as the chair of this department in the late 90s through 2000, and he was the dean of the College of Engineering and Applied Science here at the University of Colorado from, I believe, from 81 to 93, I believe was the time that he was here. So there's a direct tie to University of Colorado from your colleague, that you worked with at NASA before he left. So I have a few questions here, and I'm going to start with the very first one, because this one actually came up 5 minutes into your talk. So I decided I couldn't let this one go. So this is from Lisa Holowinski, and she asks, how can students make the most impact in their future careers?
How can they make the most impact? Well, I mean, I guess the area that your career is in depends on kind of what you're going to be working in. But I think if it's something that you really enjoy doing and everything, I think that you might be motivated to work harder at that, and might, do a bigger job in that area. But so it depends on the area you're talking about and how much you like that area. But I think we, if you liked filming and everything, you might make a huge impact making a big hit movie, or writing Hidden Figures and end up with all those awards that first book that lady wrote.
All right. So a couple more. So Avi Yonker asks, what is a piece of advice you would give other women who are looking at going into the engineering field, who might face struggles and prejudice based on their gender or race?
Yeah, I think they've got to somehow how to deal with that. I did not run into a lot of racism at NASA. I had a Jewish young lady working for me, and one day we were down the hall at a contractor's desk. He must have been in a pretty bad mood that day, because he had wiped everything off his desk onto the floor. And so I don't know what had happened. But when the two of us were standing there, he looked at us and said, the only reason either one of you are here is because of affirmative action. And so I said, well, that might be so, but I bet you ever since I've been here, I have done my job and I have done it well. And that was the end of that. So I never heard another word about it.
That's something that's, a common, as we know, that is something that often, is in the background or hovers over the head of underrepresented peoples, is that, there's always that you're only here because somebody made an exception.
Mm-hmm.
You didn't get here because you're good, and you didn't get here because you worked harder. And that's exactly why you got there, is because you worked harder. So, and you had to be good. So, I grew up with boys. Well, I had two brothers, but I also competed with, when I was in elementary school and everything, I certainly
these were all boys who lived right in my neighborhood and everything. I competed with them in school. I competed with them on riding bicycles. I competed with them skating and in all of the above. And so I was actually, maybe should I say, accustomed to competing with them. And and that might have been a difference. I actually, but I think I worked in a pretty good office. One of the lawyers, I said something about how I liked everybody I worked with and everything. One of the lawyers at work told me, well, you just haven't worked in the right place out here, because we got some very interesting places out here and everything isn't always so good at NASA, you know. And so it might have been a little different than some of the labs and everything where there were maybe a greater bit of diversity and things there. I don't know, but so the discrimination, as I thought about it, was my putting in the job I got when I got there. I thought that was discrimination, and the discrimination was my not always getting promoted at the same time or as rapidly as some of the other people did. So there was discrimination certainly in those areas.
The well-known ceiling.
Mm-hmm.
So I think what I'll do is I want to ask a question too, and then I'll get back to these. So why don't we finish out the next, if you're willing, the next 15 minutes of kind of a mix of me asking questions that the audience has sent, and a couple of questions that I'd like to ask. One of those questions I'd like to ask now before I get to the next one, and that is, you know, I wondered, you know, with the computers, and you mentioned that there were white computers and there were black computers.
Yeah.
And one of the things that I wonder, was there ever any sense of common cause of being women, or were you always, was there ever any opportunity for a sense of camaraderie with the white women, or was it always just separate?
No, when Sputnik went up and they started merging them in some offices. So I told you I went into a mixed office.
Yes.
And so.
But in that mixed office though, was it? I mean, it was mixed in terms of, you know, that you were working together. But was there ever any sense that the white women were in any way sympathetic with the, you know, the things that you were dealing with?
What do you mean things? You mean at work?
Meaning that some of the, you know, were they sympathetic to the fact that you were a black woman, and that as a black woman, there were challenges that, you know, you were having, that you dealt with on a daily basis that they may or may not have?
I don't remember us discussing those challenges that we might have encountered every day, but there was some pretty good friendly, you know, we would have luncheons together and do things together, but we probably didn't get into those discussions.
Yeah.
I'm beginning to think that there are lots of folks that don't really know a lot about what people encounter.
Yeah.
So my church group, the women, two or three groups of women got together, with black and white and everything, to discuss that. And we realized that there is not a lot of knowledge there about how people lived and what they were really encountering.
You know, it's interesting you say that, because even today, you know, my wife and I sometimes will talk and about the fact that, you know, we have good friends, you know, of all races and backgrounds and so forth. And you know, we talk about how they really don't know us. They don't know where we come from, and they don't know the experiences. I mean, because, you know, if you talk to us today, you would never, I suppose you would never have any sense of where we came from, and the things that we, you know, that we grew up with, and you know, and I have to say that's one of the things that makes I think our marriage strong, is that we have such a long shared, history of being with each other and living through things. But it's just a comment that we've made is, that we have really great friends that really don't know us.
Yeah, it takes a lot of, I guess, talking about things you've gone through and everything for people to start,
Yeah.
even though you went through them.
Yeah. So let's see. This is from, I apologize in advance if I don't pronounce this correctly. Adatya Pore. She says, thanks a lot. Your speech was very insightful and inspiring. What are your thoughts on the commercialization of the space industry with companies like SpaceX and Blue Origin entering the space? Do you think it will bring great outcomes in the long term or foster innovation even quicker than before?
Well, we certainly have seen SpaceX move fast. So he's making the decisions, and I think you see lots of times a lot of the government decisions are a lot slower because there is a sort of a bureaucracy that you have to go through to get decisions and things made. But he learned a lot from the government too, though. I would add that when these people are building these companies and doing these great things, they in many instances or several instances are hiring people who've spent years working for the government doing a lot of the same things and learning a lot of the things in addition. So I think Musk he's got the he'll make a decision, he'll do a certain thing, and I think that's good.
Okay. All right. Karen Crofton asked, I'm interested to know which technological advancement Dr. Darden has been most surprised by.
Well, listen, the first time I saw SpaceX landing the two engines there, I can tell you how many people said, well, I think they took one film and they doubled it and put it on the other side. So you think that they are coming down like that. I think a lot of people was fascinated by the fact that he was reusing those engines because he could land them, and which is actually pretty great because he's saving money by doing a lot of the things, because that's an expensive area, flying in space and everything. It's very expensive, but he is saving money by doing some of the things he's doing.
Thank you. So here's a question from William Flood. What was the reception from the engineering group like when you made the transition from the computing group to working with the engineers?
Well, the immediate group that I went to was great. And when I started, when I started actually doing the designs and all of that, I became head of, I didn't tell you all this, but I brought in all of the people in the whole country that had worked in sonic boom minimization. And we talked for a day and a half about, what's the best way to approach this. And so we decided we got the design and operation of the airplane as a factor. We got to have that area that we research. The extrapolation of the signature all the way from 40 or 50,000 feet to the ground, what happens to it? If you do all this work to shape it, would it be destroyed coming through the atmosphere? So we had to do some research like that. We went down to White Sands and measured signals at different times of the day and different turbulence levels. And the acoustics people actually says, are we measuring the right parameter in that sonic boom? Are we really hearing what disturbs the people least or best or so forth? Or is there something that we could change here? One of the things that we kept talking about was gosh, is there a composite that we could make some of these vehicles out of, such that we could change the weight of the airplane, you know, tremendously. And the problem would just be very, very different. But of course, at that time, in that year, we didn't have a composite that they would build a space vehicle out of, or airplane out of like that. So, but I do think we do some pretty fantastic things. And I guess I never tried to separate them, but when you asked the question, the two ships landing at the same time was pretty amazing.
All right, so I'm going to ask one of my questions here, and this is somewhat related to the question about SpaceX and Blue Origin, but you know, we know that companies like that have made it such that NASA is increasingly in competition for engineers, you know, that are going to those companies.
Mm-hmm.
So, do you have any thoughts on how to, you know, potentially encourage someone who's getting an aerospace engineering degree now to consider NASA?
Gosh.
Sorry about that.
I thought it was a great place. I mean, I thought it was a great place to work. And NASA has different kinds of bosses too, who actually are willing to go to bat for doing certain things that more like what you know, SpaceX and Blue Origin do. But I don't know whether the working life is much more hectic with those companies or not. That could be a factor of what is required of you and what you have to do if you're going to work for one of those private companies, which of course are still getting money from NASA.
Yeah. So here's an interesting question from Brody Cyphers. He asks, have you seen the Apple TV series considering the alternate future where Russia beat the US to the moon? What are your thoughts on the Space Force and the possible militarization of the moon?
I have not seen what you mentioned, but I have often wondered about the relationship between the companies. Yeah, if you know, if we do have lots of friction on the planets and things that we're visiting or in space, which could, I've actually thought something about that. Now, whether they're people will actually learn to try to build a better relationship, you know, such that wouldn't happen. I don't know that I've thought about that enough. Maybe you'd like to comment on that.
Oh, so, you know, in thinking about that, you know, if the Russians had made it to the moon first, I mean, they had made it in space first, and then, of course, the US caught up. You know, I think it may have created more persistence. You know, I think that the US would have certainly come close, you know, come a close second, but I think that the US would have been motivated to not just come in second, but to surpass,
Keep going.
you know, to go even further, because, you know, once the Russians were out of the race, basically, it was kind of like, okay, we've been there, done that, you know, and all right, let's do something else. And I think that, you know, one of the things this country has thrived on, and that is, you know, when there is that type of competition, particularly military competition, and I think we probably would have done more as a country, but then I don't know in terms of, you know, if there would have been a push to for private companies, you know, to
To do
get
it well.
involved because the government would have been doing all this stuff and the military. And so I think we're living in, if there was a bifurcation in time, if you go back and say, okay, you go this direction, the Russians get there first, you go this direction. I think we're on the better trajectory with the US getting there first.
And you know, we used the Russian supersonic airplane to do some tests.
Oh yeah.
I guess our vice president wanted us to support them because they hadn't been able to use it that way.
Yeah. All right. So it's now 5:29. We said that what 5:30, 5:30 our time. It's 7:30, I suppose, your time. So.
Well, I mean, I'm fine. Unless was
So
that all?
I was going to say that we can call it. We needed to have an official time to say to end, but like I said, we can, if you're willing, we can go a few more minutes, with a couple more questions.
I mean, that's fine that's fine.
But we certainly want to be able to, while we have most people on, to have them hear us say how much we appreciate this, having you as our guest this evening, and how much we treasure you as and your career and your contributions to the United States and to aerospace engineering, and also to young Black girls and boys to look at the things that you've done, and other children of color, not just Black, but other children of color, that with the 4 Ps, you can make things happen.
I really think that they helped direct me. That the fact that I had thought through that process really gave me strength and courage, I think, to take some of those steps.
So with that, I want to formally thank you, and I'm going to clap. and hope that our audience, who we can't see, will join us in clapping and acknowledging your talk and a job well done. So what we can do, having said that, how about your game? Let's go maybe another 10 minutes of answering a few more questions.
Yeah, that's fine.
Okay, so here is Catherine Hiltbrand. As women of color in STEM, we would like to ask, how do your identities as a Black woman in STEM and your 4P formula relate to each other, and what specific message would you want to share with current or future women of color in women X in color in STEM? And I can reread whatever part of that that you might need.
If I get the question right.
Well, I stumbled at there at the end, so I didn't want to distract you.
So as women, how does my career relate to the 4 Ps?
So how do you your identities as a Black woman in STEM and your 4P formula relate to each other?
Well, certainly when I said, I believe that having thought through that enabled me to take the risk and go to the director and actually ask that question. I could have gotten fired, which would have happened to me there. So I if I didn't have the 4 Ps, if I hadn't thought about the 4 Ps, I might have quit and gone to teach somewhere. I don't know, because I don't think I would, if I had to stay in the computer office in the support role all of that time without doing some other things, I might not have chosen to stay there.
All right, here's a question. I happen to know this young man, Anuba Gupta. Is undergraduate college level mathematics sufficient for work in aerospace, or one should aim for courses at master's level in applied mathematics?
Well, I did get them. It was a master's degree in applied mathematics. And then once I got into the engineering program, I was even more into the higher levels of mathematics. Yeah, I didn't. I did not tell the story about the engineer. We had spheres at Langley where they could actually generate the speeds of Mach 22, space kinds of speeds. And an engineer got the Navier-Stokes equations and actually did some derivations with them, and then brought what he had done to me to write a computer program to see if we had one sphere at a vacuum and one sphere at high pressure air with a barrier and diaphragm in between, to remove the diaphragm quickly in the computer program and be able to predict the speed of the air going into the vacuum sphere. And so he brought it to me, and I went through it and decided how I would solve it, and wrote the program. And when I got my first answers, he came in and said, no, those answers aren't right. He had some idea, of course, how the speed would be. And so I said, well, I'll go back and I'll check everything I've done and make sure I haven't made a mistake and so forth. And so I did. I went back through everything I had done, and couldn't find anything wrong. And of course, if I ran it again, it gave me the same thing. So when he came in that time, he started laughing. It's still wrong. It's still wrong, and so forth. And so I didn't particularly like his laugh. And so I said, well, so-and-so, you originally pulled out the Navier-Stokes equations and did some work. Why don't you bring me the paper that you did your work on and let me go through that to make sure a mistake wasn't made in that part of the process. So he didn't bother for anything. He went and got his papers and brought them back there. And when I went through them, I found a sign wrong. And so I tracked that sign back through what he had done and then into the computer program and changed everything that needed to be changed and ran it again. And when he came in and saw that, all he could say was, those numbers look good now. but he irritated me.
All right. Here's another question, another name that I recognize here. And Ross, before I pronounce your last name, I realize I've only called you by your first name since I've known you. So Rouse Chowdhury, what are some words of encouragement or helpful actions by others that have stuck with you in the context of what instructors, mentors, allies can do to help?
The first supervisor I had when I switched to engineering he was really, I think I liked his style. He came in and he gave me the program and said, I want you to develop this computer program and everything. If you've got any questions, I'll be next door, but otherwise do your thing. And he didn't bother me. I mean, I was left there to do the work on my own and to work. And if I had a question, I could go and ask him and he would answer the question. I had some supervisor, if I ask him, do I put a period after this sentence right here? 10 minutes later, I'm still standing there listening to the answer, kind of thing. And so I think I do like being left alone so that I can actually kind of get into what it is I'm trying to work on. So I've always appreciated that.
So Rebecca Bonamico asks, what was the experience like for you going from a truly hidden figure to getting media attention as a hidden figure branded by the book and movie?
Sometimes I think I got too many people knowing my name and stuff now. So that has been sort of a worry that maybe it's good when people don't know you and things that well. But I actually have had the opportunity since the movie came out, and I wasn't in the movie, but I started being in that group, being invited to speak to students. And so I have actually spoken to college students, female engineering students, and everything, kind of all over the country. And I was actually surprised when I had been told by a number of engineering schools that they were having difficulty trying to maintain a number of their female students. That actually surprised me, because I thought we were getting along better, because as I saw the women increasing at NASA, more coming out of engineering schools, coming to NASA and everything, and getting along with the people that we're working with, I thought that things were improving, but that wasn't necessarily so. And I've been told in some instances it is the classmates that are doing the bothering, and in other instances it's the professors doing the bothering.
Well, Dr. Darden, Dr. Christine Darden, I think it's 5:40, and so in the interest of time and the fact you're on the East Coast, I again want to thank you, and on behalf of the students and faculty and staff here at the University of Colorado, thank you. And at this point, I'll turn it back over to Tanya to close things out. And again, much appreciated.
Well, thank you. I appreciate your handling the questions. I missed your, what was that you were supposed to do? You were supposed to have an interview.
Oh, we did it. We did it. It was just
a little bit of it, huh?
It was mixed in with all the other questions.
Okay. Well, it's been great. It's been great seeing you again and meeting you. I didn't know Dr. Seabass that well, but he did he came by my office a couple of times, and he was at the meeting when we had everybody there.
Well, one quick question before I turn over to Tanya. Were you at the kickoff meeting for the DARPA QSP program?
No, I wasn't.
Okay, because that was, as we discussed, that's when I got involved directly with the sonic and was, learning about your work after, Richard Seabass had introduced me to you something like 5 years before that. But yeah, so that DARPA was where I kind of started getting involved. So,
yeah.
But
I know I think I went to one of the earlier meetings that they had out
one of the technical exchange meetings.
Yeah, out in California somewhere.
Oh yeah. So we probably crossed paths there also.
Might have. Well, right. because well, some of the people were suggesting that we do some things that we had already done because they didn't know about it.
Yes.
And I came out there with Peter then.
Yes.
And I told him, I said, well, maybe you need to start explaining a little bit what has been done and kind of what the results was or something.
Well, I told you how that was received when I suggested that at the kickoff. So, but you and I can have that continue that discussion later because yeah, Peter and I, like I said, we still agree to disagree. All right, I'll leave it at that.
Okay. Okay.
Well, thank you, Dr. Darden. I want to thank you for your time today and for sharing your experience and your wisdom with us. We didn't get to all the questions, which tells you there was a lot of interest in your experience. And so I hope this isn't the last time we have you at CU. Actually there's another opportunity for you to come after the pandemic. We can do something in person. I would really love to have you back.
Well, that's true. I actually spent a long time in Colorado with Janet out there. A couple of times I've spent some time out there, helped them move back to Georgia. And then, so I helped take care of the boys while she was commuting from Colorado Springs to Denver to Cheyenne, Wyoming.
Well, we appreciate it, and that's the way I was connected with you. I did meet your wonderful daughter, Janet, and I appreciate her connecting us for this talk today. So thank you to everybody who joined. I know there's some people who left. And sorry that we couldn't get through all the questions, but I hope this talk was a very meaningful and enlightening experience for you all. And hopefully we'll be able to do more of these. And so thank you all for joining, and hope you all have a great night. And thank you, Dr. Argo, for everything. Grace Wilson and everybody who's responsible for making sure this webinar happened. Thank you.
Thank you all.
Thank you.
Good night.